So after discussing the DC models, right, for PMOS and NMOS, it would be interesting to see first that the application of that, right, in a very simple circuit which we have talked about. So that circuit which you would have seen where we connect the NMOS to the bottom, right, and while the drain of the two NMOS and PMOS are connected, while the source is applied to VDD and the gates are shorted and drain are shorted, right? And the output is taken at the drain end. So in this circuit, one question we were also discussing, if we switch the two, what would be the so what would be the output, right? If we switch the NMOS and PMOS. So in this particular circuit, which we see, right, if we the one thing would be that what is the range of V in which we will change is the 0 to VDD, right? Because this is the maximum voltage which we have applied to our circuit, right? So maximum voltage which is applied, maximum applied voltage, and the minimum applied voltage which we have is the ground, right? So you are applying the V in, which is between these two ranges, so 0 to VDD, right? And now our thing is that we want to see how the output of V out changes for this particular circuit, right? That's what we were discussing. So let's start simply. If this is my V in, which I'm going to vary between 0 and VDD, right? This is the range, and this is my V out, which I'm plotting, right? Or want to plot. So now let's see what happens. So initially when our V in is 0, right? So when your V in is 0, what happens? We clearly see that the VGS across this part, so this is our VGS of NFET, and this is our VSG of PFET. So if V in is 0, we see that VSG of P is VDD, right? While VGSN is 0. So this is clearly that the PMOS is on while your NMOS is off, right? So when NMOS is off, what one can see is that there is no current flowing through the NMOS. So when there is no current flowing through the NMOS and PMOS is on, that means this node V out would try to be close to VDD. But there is nothing which is sinking the current, right? So the current is only flowing through to the node VDD. So what would happen is that your V out in this case would be VDD, right? Because this transistor is not on at all. And now what happens? So till when does it? So now if we increase V in, what happens? Does it remain VDD or would change? The question is that when does the PMOS or sorry NMOS gets on? Because this will remain VDD until your NMOS gets or turns on, right? Because until NMOS turns on, there is no part to sink. So that means, and when is the NMOS getting turned on? When VGS becomes equal to VT. That means when V in becomes equal to VTN. Till that point, we see that your output voltage remains nearly VDD, right? So in this case, you understand that we are assuming that there is the current for is nearly 0 when VGSN is less than VTN, right? Because there is no leakage or nearly zero leakage is what we are assuming. So what happens when it turns on? It turns on, we see that it sees a very monumental VDS across it, and VGS is just, so the overdrive is just getting, it's very close to 0, right? So that is what, because you see that overdrive VGSN minus VTN, right? Which would be basically your V in minus VTN. So at this point in this region, we see which is above VTN, your NMOS is going to have a very small overdrive, but a huge VDS. So which region would that be in? So clearly that would be in saturation region. So if we say this is your M1 and this is your M2, we know that M in this, what is happening? M2 is on, M1 is off, and as soon as this turns on NMOS, it finds itself in saturation region. And what happens to PMOS? PMOS is also, because PMOS, it was shorted, so then it is turned on, but V out now is decreasing. So that means VSD is now building up slowly, while VSG is huge, right? So it finds itself in linear region. So in this part, we see that it starts to decrease. And why is it decreasing? Because now there is a sinking path, right? And in this region, we see it finds M2 in linear and M1 in saturation. Now what is happening? Your V in is increasing, that means VSG is decreasing. And when VSG is decreasing, at the same time, V out is also decreasing because your M1 current is becoming strong and strong. So because of that, at certain point, you would see that your, if these are two same size, you will see at certain point that these two transistor will find itself in saturation. So both these transistor would be in saturation. This is the point at which you will see a huge drop, right? Like this. And then you see what happens. Then after this saturation, now because the V out is decreasing a lot, your M1 goes to linear, right? M2 is, what is the condition with M2? Because your VDS is now huge, right? Because your VDD minus V out is huge. And your V in is increasing, so your VSG is not there. You will see that it starts to, your M2 becomes in saturation, right? It remains in saturation, M1 becomes linear, and then you see slowly what happens, that your M2, because M1 is becoming linear while M2 is saturating. And when the M2 V out is becoming large and V in is also increasing, which decreases the VSG, at certain point you see when VSG P becomes less than mod of VTP, what happens? Your M2 turns off. And when your M2 turns off, now your V out would be completely discharged by your M1, right? So that is the part which you will see going like this here. Okay. So I'm just very approximately drawing it, but I will show you in the curve how it looks like, right? How it is the other way of drawing it. Okay, so then in this region, we would see that when there is VDD minus VTP, uh, your M2 has turned off, right? And M1 is in linear, right? And it is going towards deep triode, right? Because your this part is decreasing. So in the end, this is what is the basic DC characteristics of this particular CMOS inverter. And one can see clearly if, as we were discussing, that if we divide it in three regions, right? So this is region 1, let's say, this is region 2, and this is region 3. So in region 1 and 3, right, we see your dV out by dV in mod of this is much smaller, right? Either it is 0, as it is the case in the first region, or it is very small. So this is the derivative which we are taking. And why we are interested in derivative? Because we just want to see that how the V out is changing with V in if we apply small V in. So now that means, but in region 2, it's very surprising to see that your dV out by dV in is quite large, right? It's huge because the dV out is changing very fast with very small change in V in. And that is one of the key of when we see this interplay of that when MOSFET is in saturation region, both MOSFETs are in saturation region, what interestingly you see is your gain or this dV out by dV in which you get is much, much larger, which gives you a hope to design an amplifier, which is what we were talking about. So that means if we want to use the circuit as an amplifier, what you would do, this is my V out, this is my V in, and what are we amplifying? Obviously a small signal which is very weak. So if we are interested in amplifying a signal which is weak, where do we need to go? We need to be working in this region, right? This is your region 2 which we said. And where would you put this signal? So you have a signal. So this is obviously 0 to VDD, right? So with VDD is 1.8 volt. And we have a signal which is coming from microphone, let's say, as we talked about. This is few millivolts, right? Or let's say 100 microvolt. That is the V versus T we are talking about. So now, where would I put this in? Right? So because first of all, I know that clearly that in region 1 and 3, if I put this directly here, this signal, it is useless because there is no gain in this region, right? So I have to put this signal in this region. Now to put this into this region, that means I have to first come to this region. And how do I come to this region? When I apply a certain DC voltage. So to arrive at this region, I have to apply this DC voltage, which is V in, right? Now this DC voltage, then if I come in this region, which is what I know as biasing, that I bias this transistor in this region, when I apply sufficient V in and come to this region, then what I could do is I could overlap what I'm getting from microphone. So like this. So let's say this is from microphone what I'm getting. And when I overlap this, what I see, because of this large gain in this region, my signal becomes amplified as a result of this large slope which is happening here, right? But the only thing which I have to do now to make it work, I have to give a DC, and on top of that I was giving this small AC. So this is my capital V in and this is my small V in. So this is how we represent the small signal which is coming from a source, and this is the DC which you have to apply to go to that region. So that's why we say the total signal, which is small subscript and capital V in, equal to your V in small and both small. So this is your DC bias and this is your small signal, right? So now in the next video, we'll see how to evaluate if we have a signal and I want to know how much my signal has amplified, right? So how do I do that kind of calculation?